of our FDP. So first I will introduce him. He received his BTech degree in Electronics and Communication Engineering from Jawaharlal Nehru Technological University, Karnataka, Andhra Pradesh. Kaninada, Andhra Pradesh in India 2014. Completed MTech degree in VLSI Design from ABV, Indian Institute of Information Technology and Management, ABV IIITM, Madhya Pradesh, India in 2016. He received PhD degree in Electronics and Communication Engineering from National Institute of Technology, Karnataka in 2021. He was a visiting PhD scholar for 16 months at Estimation Tracking and Fusion, ETF Laboratory, McMaster University, Canada, under the supervision of Professor T. Kurubarajan during the 2018-19. In addition, he was also a visiting researcher as part of Indo-Norwegian collaboration to Autonomous and Cyber Physical Systems ACPS Research Group, Department of Information and Communication Technology ICT, University of Agder, Norway, under the supervision of Professor Linga Reddy during 2021-22. After his PhD, he worked for 2 years as a technical specialist in the ADAS department in Continental Autonomous Mobility India Private Limited, India. Currently working as postdoc fellow in ICT department, University of Agder, Norway. He was a recipient of Sir C.V. Raman Award from Institution of Engineering and Technology, IIT, for outstanding academics and research. Received best PhD thesis in 2022 in graduate thesis evaluation in 7 minutes from IEEE ComSoc Graduate Congress. In addition, he received IEEE ITS Research Excellence Award in 2023 from IEEE Information Theory Society, ITS Bangalore chapter. Moreover, receipt of Pratsahan Award from IEEE ComSoc and Best Paper recognition from IEEE conferences. His research interests include intentional interference to autonomous sensors, target tracking, and information fusion. Sir will give today's talk on what is actually generative AI, and also I requested him to include autoencoders and variational autoencoders. So I think he's starting with this because his first slide is autoencoders and variational autoencoders that are very useful for generative AI actually. And then I think he will start with the generative AI. And again, I welcome him and I request him to take over the session.
Hi. Thank you. First of all, thanks for giving an opportunity. Yeah, so far in this FTP, this is the 4th day, and I was seeing since it's like a Gen AI topic, most of the professors are coming in and then started telling about exactness of Gen AI applications and all the stuff. And yeah, even some sort of tutorial, some experimental works are being demonstrated and everything. But this one is this piece of work, whatever I'm going to present, it might be something a bit like in a mathematical way, so that understanding a preliminary mathematical stuff, what exactly working behind the Gen AI is more important, I believe. So accordingly, I prepared my slides. So yeah, if someone feels like not having too much images or videos or theory, please forgive me in that regard, but this could be helpful. So my topic will directly jump into autoencoder, because everyone know autoencoder was the one backbone which stands in Gen AI for creating all sorts of images, videos, whatever we are seeing in. It's basically a encoder decoder model where from the bigger data set, a latent space can be created, and then the latent space is obviously decoded to give sort of images or videos, whatever we are requesting. So it is the base model of autoencoder, which started maybe 15 years back. And I would like to stretch up on more on variational thing. Why? Because autoencoders are not exactly the great. It's just like image taking and image giving process, so which is of not that much use. except in communication protocols. But so my slides will go in a first slide will be like in a autoencoder, and then I will tell like why they move to denoising autoencoder model, and then directly into variational encoder, and there we will try to spend some time in a variational autoencoder, the kind of mathematical function or the loss function, how it is actually running behind. And to explain the loss function, I will go through two main steps in our autoencoder, like KL divergence and then repair parameterization trick. So those are the actual key components which are really running the autoencoders nowadays. And I will go through the overview, and maybe I hope by that time we reach the sixth bulletin point, our FTP will get closed. In case if we have time, we will see the variants of actual VAV, like beta variation and then VQ variations. So let's go. These are the preliminary notations we are going to use throughout the lecture. And we know like whatever the data samples we are having, all the data samples together we call as a data set. So here, whenever I say like X or like an image, it means like a sample we are taking from the data set D. So let us assume we have some 100 images, and then out of 100 images, if I'm picking one, we call that one as like a data point or like a data sample X. And within that one, an image, for example, if you take an image is a 2D information, which can be like somewhere around 100 cross 100. So there will be a data point. So it called as a data point. And the tilde will be used for corrupted version, and then dash will be used for the reconstructed version. So X dash is our actual goal in a Gen AI. So these are the things we are going to use. And for encoding and decoding, I'm just using the nomenclature of G and F, the standard nomenclatures. So first of all, we will see like what autoencoder is like. Autoencoder is just a encoder decoder model which will try to reconstruct the input data. So whatever the input data we give, it will try to reconstruct it. There is no such Gen AI principle in it. So it is not going to create any new generation there. So if you are just giving a number one, it will be like only one. It is not going to make any stylish font or like base fonts or any other color font or anything. No such things. It's like just a reconstruction of the input data. So if you see, this is how a autoencoder usually looks like. We have a data set from the data set, and then we have a sample of X. Whenever we have a sample, and then it is going through the encoder model, and then obviously we have on the right side we have a decoder model and then reconstructed image. If you clearly see here, they're like we are giving a number 4 and we are retrieving the same. So there is no such a huge thing is going to happen here. So from our space, space X, it is going to have a lower dimensional space there. Whatever the bottleneck was written, it is something called as a feature we call as a feature, or like subspace, or like a latent space. Even smaller spaces we call, usually in different papers they have different nomenclature, but which we call as like a lower dimensional space usually. So the higher dimensional space is going through the encoder model, and then it is going to create a lower dimensional model, lower dimensional data representation, or like a feature, so which is actually responsible to capture the whole data information from the actual X. And then if you see, if you see on the right side, you have a decoder model, which is responsible to decode the information from that low latency, low dimensional feature vectors, or and then able to create an X dash or like reconstructed image. This is how the autoencoder usually looks like. So in a glimpse, encoder network translates original higher dimensional input to lower dimension, and decoder, it's just a decodes the network, recovers the data from the code, likely with a larger output layers. So at the end, we are having a larger output layers. This is what typical autoencoder structure look like. So whatever the autoencoder looks like in the current forms are like, there are some 20-30 variants are there. All of them looks alike. There is no such a great change will be there, except in the loss functions. So this encoder network essentially accomplishes the dimensional reduction. Usually it can be done using a principal component analysis or matrix factorization. Those are like key steps for the dimensional reductions. In addition, the autoencoder is explicitly optimized for the data reconstruction from the code. Yeah. So, and then we will see the kind of a nomenclature here. The model contains an encoder function. I call the encoder function as a g of phi, and then here the phi, whatever you are seeing, it's like a parameterized by phi, or like we can call them as a, in a neural network sense, we call them as a weights and biases. So all the weights and biases corresponding to encoder, we are just defining by the phi. And then decoder function, we are telling like a f, and which is parameterized by the theta. So whenever you want to recover like a x dash, so x dash is coming only from the x, so x should undergo through the encoding model. So g phi of x, it will compute, and then it will go through decoder, so which is like f theta of g phi of x is called as a reconstructed input. So now we will see how exactly it looks like. Yeah. So if you see exactly like at the output x dash, so x dash is something like x, which is going through the g of phi, and then this g of phi into x, which is going through the f like parameterized. So this is the output. So whenever you see this kind of function, it's like a defined superscript I, so which is like a data sample. So all the data samples are being considered here, like all the n data samples, and then it is simply a squared one, so which is an MSE. So for initial auto encoders, the mathematical loss function, whatever they provide, is just like MSE. Just you have a sample, and then it gone through the process, and you have a x dash. So with the x and x dash, we are just going to compute the uh, MSE. Okay, and this is how it usually look like. But why this autoencoders really plays an important role, we will see now. So whenever you are seeing like a autoencoder architecture, they come up with a variant called as a denoising autoencoder. So whatever the preliminary autoencoder we have, the original input x is like, if you see on the left side, the 4. Uh, Someone please tell like, am I enabling my red font or something? Like whether someone is able to see my cursor on the screen?
Yes, sir.
Okay, 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 yeah.
We are able to see.
Okay, okay, then it's fine. So here, if you see exactly, the original input is like x, all the data samples correspond to the 4. Usually, this kind of model was not there in an autoencoder, and then they come up with something called as like a partially destroy some of the inputs, or like make some noise out of it, or like corrupt them with the noise, and then try to do the same job again. I mean, encode and then decode, and then try to get the thing. But here something obviously something is happening, so which is called as like a denoising thing. So since the autoencoder learns to identify the function, we are facing the risk of overfitting. In the preliminary autoencoder, we have a problem of like overfitting, where there are more network parameters than the number of data points. But to avoid overfitting and improve the robustness, denoising autoencoders were proposed in 2008, and which is a basic modification to the autoencoder we discussed earlier. The input is partially corrupted by adding noises to make that values like input value are more in a stochastic manner. So we have more corrupted noise. Then the model is trained to recover the original input. So this is one beautiful thing. So whenever you see the loss function again looks the MSC thing. So which is like the same, like that you have a true data samples and the noisy data samples, and then you are trying to recover the actual information from the corrupted ones, and it works. uh, this design is motivated by the fact that the humans can easily recognize an object or a scene, even the view is partially occluded. So this is what exactly happens with the humans. So this concept is called as like a repair. So in denoising autoencoders, the repair will happen. To repair the partially destroyed input, or like the denoising autoencoder has to discover and capture the relationships between the dimensions of input, and then it have to infer the missing pieces. This is the one thing happened with a denoising autoencoder. And uh, like if you see in a research topics, people come up with a different noise models, and uh, different things had happened. Like they tried with the noise models, and then they tried to drop some of the nodes, I mean initial inputs, and how that's how they progressed the thing. But this really doesn't make more sense, just because it is avoiding overfitting problem, and then it is able to recover the data, but it is not generating the data. So there is a need to generate the data. So that's where the autoencoders are modified to variational autoencoders. So now we have something called as a variational autoencoders, which was given in 2014 by Kingma, and who is one of the prominent researcher who involved in Adam optimizer, what we are using right now, which is the breakthrough in machine learning. And here the thing is like, they want to see something like, they don't want to play with any points anymore, like the random points or something. They want to do everything with the density. So here, rather than the problem changed from here, see if you see the problem, the solid line, initially the solid lines was the actual encoder model. The solid lines used to generate distribution, and then now it changed to in this way, like the dashed lines, it's called the distribution. So now we are not going to deal with the points, rather than that one we are going to deal our problem with the distributions. So that's why I'm like telling, like you have a prior, and then we have a likelihood and posterior. So this likelihood is something like p of x given z. X is like our measurement here, like image. So uh, I mean the hidden vectors, whatever. So given a hidden vector, if you are trying to reformulate the image, we call that one as a likelihood. And similarly, given a image, if you are trying to if you are try to find the hidden layer, or like the bottleneck of z, then we call that as a posterior. So here the work is basically developed on the posteriors. And yeah, and in a variational autoencoders, they come up with interesting ideas, like how we can approximate the posterior, and then so on. So now if you see, instead of mapping the input into a fixed vector, we want to map it into a distribution. Now the problem is changed to a distribution rather than a vector. uh, so here you will be seeing everything in terms of a Gaussianity, like having some mean and the variances kind of thing. Like so if you go through it, so rather than having a point kind of things, now the thing is changed to distribution. So this is how the variational autoencoder architectures usually look like. uh, is this the same block? So whatever encoder model we were seeing previously, it's a similar one, but I will explain in deep, like why it is called as like a probabilistic encoder, and rather than having a simple encoder model, why they are coming with a mu and a sigma kind of thing. We will see that one shortly. But and here the one more interesting thing is like the probabilistic decoder. The probabilistic decoder is one which is responsible to give the probability, I mean joint probability of x given z. Like when you have a z, or like a sample latent space, your interest is to generate the xz xx. So here on the right side, if you see, this is where the variational autoencoder really making more sense. For example, from the x, if you are able to come with to z, like the latent space, and if you're providing the same latent space z, then you will get again the x. But our interest is not like that. So we want to tamper this z just by making a more probabilistic encoder. So if you see here, whatever value z is equal to mu plus sigma, so from the data sample, and then they are having another parameter epsilon. So whenever you have another parameter of epsilon, the data variability will come into picture in initial stage. So rather than having the actual image query, you will be having a slightly different image query, and then regarding that image query, you will be having a another image. So this is not going to give a new whole set of new image. For example, if your data set contains a humans, and if you are requesting a dog, no, it is not going to happen. So it is going to learn from the same space, but the output what you are expecting is something a bit different from the space. It's like a very small nominal difference will be there. So if you are querying for the, I mean, if your data set contains the humans, and then you are supposed to ask for the humans with maybe some gray color hair, or like some hair modification, or like smile, or like more color gradient, such kind of things. This is how the variational autoencoder uh, works. But whenever we see the autoencoder, the loss is kind of different. So the overall loss function have two components here. So previously we were seeing like the loss function is just an MSE, but here it's not the same. But here we have two loss functions. I mean, the loss function is component of two components. One is like a reconstruction loss, and another one called as a KL divergence loss. So the first one, the reconstruction loss, will tell like measures how well the encoder reconstructs the input data. So it will tell like how well it is going to give the encoder data. So which is almost like MSE. So this one, whatever you are seeing, expectation of log of p x given z, it is a MSE. And then there is another need of quantification, this probabilistic decoder. So the to know the probabilistic decoder behavior, we have something called KL divergence loss, which will regularize our latent space, and then it will try to match your posterior, I mean, prior distribution. So whatever you are finding at the decoding level, so it will try to match it to the prior distribution. How it can be done? This is going to be done in a KL divergence sense. KL divergence is something like if you given with a two distributions, it will try to tell like how well they are similar. Like if you are giving one distribution with a Gaussian and another one with some Rayleigh, it will tell like no, they are not having good match. But if you are giving two Gaussians, then it will highly likely to tell like okay, they are matching. So this matching, whatever word I'm telling, the KL divergence loss. So the loss will be some certain number which is like greater than 0. So it will tell like okay, 0, 0 0.4, 0 0.6, how well the match is being happening. For a maybe for a image processing people, they know some matrices like SSIM, GSIM kind of thing. So structural similarity, gradient similarity. So they are going to get some kind of match in the role of 0 to 1, which is in a image spaces. Similarly, whenever you have a data in a data space, we have something called a divergence loss, KL divergence loss, which will tell like how well the two distributions are uh, closer, or like how approximately they are near. So this is the one good thing with the KL divergence. So in a variational encoders, they come up with the overall loss as a function of a reconstruction loss and then a KL divergence loss. So I'm sorry, a reconstruction loss. So this reconstruction loss is usually for a I mean, the reconstruction loss is something like an MSC. There is no need to figure out much here. But whenever coming to KL divergence loss, for the KL divergence loss, you have KL divergence. So whatever mean and sigma you are having. So this is how the formula it was given. But we will see shortly the kind of derivation. So what is KL divergence? So in the KL divergence, what is happening? You are trying to, I mean, in encoder decoder model, our decoder is trying to work with a distribution. So this KL divergence measures the difference between two probability distributions of P of x and Q of x. So this P of x and Q of x in the sense, so here whatever the Q of x you are going to generate, uh, whether it is a really good enough match with the P of x generating here. So you can think of this sense. So to do this one, you have a formula like a KL divergence. It will tell like the expectation of log of P given Q, and P of x and Q of x are the probability distributions over here. And it will tell like how, it will just tell you like how appropriate or like how approximation is being done with the P and Q. And similarly, for example, if P and Q, if you are doing, and similarly you can do for Q and X as well. So for example, if you're telling KL divergence of a Q and P, then it should be written in a different way, expectation over Q and then log of Q whole divided by X. This is how the formula will change. So whenever you're approximating one with another, so the whole scenario will going to change. The KL divergence of a P given Q is not equal to Q given X. We will see now. Okay. For example, I am taking two probability distributions, like one with a random variable 0, 1, 2, and which is having a happening of a 0.36, 0.48, and 0.16. And similarly, I have another event of Q, and the PDF follows like this: the random variable of 0, 1, 2, and then they are following a uniform distribution of 1 by 3. Whenever I want to find like how likely the Q with a P, then I'm making a query like uh, KL divergence of P given Q. The formula looks like P of X log of P given Q. So instead of taking P of X, P of X, you can take 0.36 log of P by Q, and again 0.48 times log of P by Q, and then 0.16 log of P by X. Whenever you compute, you will get some number. So here I'm just doing a KL divergence of Q given P. So whenever I'm substituting as 1 over 3 ln of the value, and then again, so I'll be getting somewhere around 0.09, which is like almost near to 1. So this will tells me like the uniform distribution, whatever you are having at a Q, it is having very good match with the P. So this is how the KL divergence usually tell you. So this value varies from, yeah, so this value is like greater than 0 every time, whether you are making a divergence from P to Q or Q to P, that doesn't matter, but it's always a positive quantity. And uh, and whenever you are doing the KL divergence, P given Q or like a Q given P, they are not equal. So we always try to tend in different way. Like you should be knowing this asymmetric property. No. First, we will see like a derivation, like how they're coming with this kind of expression, KL divergence expression in a network. So we will try to see a Gaussian distribution. It's pretty simple here. Like whenever you are finding the uniform distribution, I was telling like a uniform distribution is there, and then we are having some certain values. Doing numerically is kind of easy, but a generic model needs to be required. And most of the time, we always make an assumptions like the data is in Gaussian in nature. So we will make a proper derivation for with a Gaussian assumptions. So let us take like we have only two uh, variables, and like a P and Q, the PDFs of sigma, mu1 and sigma1, STD. And similarly, you have another Gaussian with a mean and the variance. So whenever you have these things, you need to find the KL divergence. The KL divergence, I'm querying like KL divergence of a P given Q. So I just want to quantify my P given the Q. So I'm assuming like Q is at an encoder, and then P is my actual output I am going to see at the decoder. So which is an uh, we call even the integration model you're seeing, we can read that one as an expectation, the expectation of uh, P of X log of P given Q, P given Q. And then, so since it's a Gaussian, we can write in a pretty standard format, like 1 by square root of 2 pi and std square, and then exponential of x minus mu, the x minus the mean, and then whole divided by the standard deviations. So this is how the P and Q of X are like being modeled standard. And then in the query model, you can see uh, yeah, log of P by Q is there. So there is a log term, and then P of X, and then Q of X. And then we need to solve this log, and then you have to try to give an expectation over the things. So on expanding the logarithm, since it's a exponential function, like you will be end up with means and the standard deviations, and then whatever the square root term you were seeing, like sigma 2 by sigma 1 was remain still there. And then once you substitute this whole term, like log term into this one, then you will be getting a KL formula, like KL. So here there is an intuition to look into. So there is a logarithm of sigma 2 given by sigma 1, right? So which will obviously tell like if your the decoded image is like having more noisy. So if it is like more noisy in nature, so obviously it will be like more noise term will incorporate over here, so which we don't want most of the time. and then since whenever you are applying the expectation internally, so expectation of x minus mu is like a sigma 1, and then expectation of x minus mu we can write in terms of a sigma 1 again, so sigma 1 plus mu 1 minus mu 2. On substitution we can get into this format. So but if you clearly observe this one, it's a pretty much intuitive thing. So whatever the means, I mean, there is means are there, like the means are getting subtracted, and then whatever the query you have, the query will be in a denominator, and then on rearranging we can get something like log of sigma 2 by sigma 1, this kind. And here if you see there's still like this minus 1. uh, the reason because of this minus 1 is the dimensionality. Since we are modeling with the only one dimension, like we are taking only the single dimension model PDF, so we end up with a minus 1. In case if you are taking with a multi-dimensional, I mean multivariant thing, then this number will change to your dimensionality number. For example, if it is like a k dimensional one, then it's like a k. And similarly if you see here, like since it's like a pretty much uni1, and then having the std and mean, so we are getting only std squares over here, like standard deviation squares. But in that case it will be like a covariance. uh, okay, so whenever you see like the Gaussian distributions, uh, with a small example, let us assume we have two distributions, with a one with mean 0 and then standard deviation of 1, and another one with like a mean of 2 and then a standard deviation. By just by knowing, seeing this thing, we can able to tell something very intuitive, like okay, this standard deviation is ending at 1, and then its mean is like somewhere else 2, and then it is covering whole lot of information, uh, whole lot of information. So my query is like KL divergence of P given Q is giving somewhere around 0.47, so which is not that good. So in this case if you see whatever you are getting, it is telling like both are uniform in nature and both are having good match. But here if you see, it is telling like both are having some match, and but the value is like slightly high. So this is the kind of summary we have in a KL divergence. It will tell like how one distribution diverges from another, or like one distribution is like a good match with another. And the KL divergence is having a closed form solution, since it's like a pretty much in an exponential form and logarithmic forms. It's a closed form solution do occur, and there is no need of optimizations, since we are playing with the unimodels. And this value is always a non-negative quantity, and KL divergence of P given Q is not equal to KL divergence of Q given P. So now we will try to expand the same thing to the multivariant Gaussian. In a multivariant Gaussian, we are assuming like we have a multivariant of uh, I mean stacked mu of mu1, and then its covariance vectors or covariance matrix of sigma. I mean it's like the bigger sigma. So now if you have a two multivariant Gaussian distributions, and we will try to see the same KL divergence definition, how it's going to happen. So here I'm just writing an expectation of P of X, since we are working with the multidimensional things, and logarithm of P by Q. And the PDFs of the multivariant we can write, since they are all are like means. So the mu1 is a vector which represents all the all the means of the single variant Gaussians, and its corresponding covariance is given by sigma. So this is how a PDF of multivariant looks like. On solving, whenever we're just trying to solve the whole thing, is the same thing. So there you were getting like a sigma 2 by sigma 1. Here it's like a covariance matrix. I mean the determinant of the covariances is the same, and then again you will be end up with the terms like there you will be seeing what is the deviation of your mean exactly. So it's the same x minus mu terms will be there. So on solving, we will try to use some of the quadratic terms, where we know like expectation of x minus mu and x minus mu transpose is always a constant with the dimensionality d. So whatever the whatever dimension we will take, we are assuming like it's a d-dimensional multivariant thing, so it will come with the d. And for the same thing, you can also tell like the you can use some of the quadratic terms like the traces and everything. On substitution we'll be trying to get KL divergence over here. So here the KL divergence is the same like log there, log of sigma 2 by sigma 1. Here it's a log of determinant of covariance matrix, whatever we are seeing at the 2 is over 1, I mean q by 1. And here the term is like the traces term is coming into picture, and then this minus d will tells like what is the dimensionality of that particular multivariant. And this key insights like here the covariance, even though you have your means and some set of means and covariances, this covariance alignment through the log determinant and the trace terms is pretty much easy. And this mean element can be happening only with the quadratic terms, so solving these things are easy. But here uh, the thing is like it is in a higher dimensional space, so we need more computational power to solve these kind of things. Rather than this one, the everything was like pretty standard in deriving the KL divergence. So this is so now we are in a position like, okay, rather than having this point kind of thing, we change the whole scenario to the PDF. And then we know like what are the PDF we are going to generate, how to match the PDF with the previously generated PDF. But whenever you see the actual architecture, whatever I was showing before, it is having two different terms. Like at encoder model, we are calling that one as like a probabilistic encoder, and there is a like a mu and sigma kind of things. So why exactly this kind of thing happens, we will try to see. Also in a loss function, we have the two loss functions. We were seeing like it's a combination of KL divergence and the encoder one. So this reparameterization trick was the one which will really helping to generate the model like whatever uh, the current era we are seeing, it's all possible only because of this reparameterization trick. So this VAE samples the latent variable z, like the hidden space from the distribution q of z given x. But how this is going to happen, like it is just introducing a stochasticity just by making it a, I mean just by making a smaller manipulation called as a reparameterization trick. And this reparameterization trick is the one which is allowing us to make a proper back, I mean back tracing or like the gradient kind of thing. So that is the one beautiful thing happened in variational autoencoders, which will allow us to make back propagation, and it is not challenging anymore in these things. And this reparameterization trick reformulates the sampling process to enable the back propagation, as we said. So how this reparameterization trick is going to happen? So uh, whatever the hidden space we are having z, instead of directly sampling the z from mu and sigma, we are not going to do in this way. Rather than it, we will take the mu and sigma, and then we will have a element wise operation with an epsilon. So this will make another whole set of differentiable function with a mu and sigma. So this kind of trick is called then as a reparameterization trick. And since once you apply reparameterization, you have a different values and it's having a stochasticness, and then it will allows you to make a back propagation more easy. So the mathematics behind the trick is pretty much simple. The encoder gives an outputs like mu and sigma for the trained data set, trained data sample, defining the to define the latent distribution. So in this distribution, we are going to take like z as a parameter of mu comma sigma. But here, whenever it comes to make a sample in a bottleneck, or like rather than making a direct sampling, we are just doing like mu plus sigma times of epsilon. This is how the reparameterization trick is being happened in variational autoencoders. And the intuition, what exact intuition is there? this will trick separates the stochasticity from the parameters. Now it is not no more in a parameter business for us. And this random variable introduces the randomness. So here you can see like the epsilon, whatever I'm telling, this epsilon is the one key thing with a random variable. So we are going to fetch the random variable every time, and then it is going to multiply it with the sigma. So every time, rather than having mu and sigma, you will be getting with a mu and different sigma. So if it is the if the random variable is like every time I'm telling like it's a unity epsilon, then it will work as like a usual autoencoders. But now since we are having a random variable over here, it will be working as a probability I mean distribution kind of thing. So this is the one thing. And again, the important thing is like since the mu and sigma remains deterministic, it allows the gradient flow, and optimizations are like pretty much easy here. uh, yeah, this is the kind of it's not, I should not say algo. So the encoder is responsible to give the mu and sigma, and then the reparameterization is responsible to create a latent space z with the random variable I mean epsilon, and then this z will be passed to the decoder model to get a fine tuned or like whatever the query of x dash, or like a generated image, or like generated data space. And this whole thing is being optimized with the two things. One is called the reconstruction loss, and then another one is like a KL divergence. KL divergence is responsible for matching the PDFs, or like tell how how much deviation was there between the actual PDFs. And then this reconstruction loss, one responsible for telling how good is your encoding model, which is pretty much messy. Yeah, yeah. And these are the benefits we just discussed. And then to visualize the trick, this is how it happened. So in a simple autoencoder, you have this phi and x, and then it is directly contributing to the z. But here it is not going to happen. You are having an epsilon which is creating a random variable, and then it is being multiplied with the sigma, and then it is responsible to give z. So it is like every time it's the same thing happening, and you will be getting a new value every time. So yeah, the back propagation is allowing us. So the same trick was being used in several papers, and this is a kind of a standard one right now. But there are few challenges uh, in a reparameterization, which we will talk in a while. And but one thing is like the kind of model parameter, like we were telling like the epsilon can be done, but how much epsilon we need to take is one meaningful tuning parameter for a whole system. So far we have seen like what is variational autoencoder, which is a type of generative model. Encoded data into latent space, so which we call like a z bottleneck, and this reconstructions are generates new data by decoding the latent space. The latent space will be decoded, and then rather than autoencoders, this one is something like more probabilistic model was being introduced in a variational autoencoder. And whenever coming to the working space, it's like the same encoder is responsible, but the randomness was given with the uh, was incorporated to make it more distribution in nature to give the z. And then the latent space is always more in a pdf way, and then the decoder is working in the same way. And then this is all okay. And the key concepts you need to learn in a VAE is something more about the regularization trick or whatever happening, and then whatever parameterization trick happening. So the KL divergence is it is only the key thing which is ensuring the latent space is aligning with the prior distribution, so that it will make proper match. And then the reparameterization trick which will making us possible to make a back propagation. So these two are the key components in a VA. And nowadays we are seeing variational autoencoders in a whole lot of image generation data. manipulations are like new data creations or latent space explorations, anomaly detections, and semi-supervised learnings. These are the few of the applications, but these are not limited. And so far in FTP, whatever almost all applications we were seeing, all can be solved in a variational autoencoder model. But to this extent, if variational autoencoders can do, then why we are not using variational autoencoders? That's the first question we get. So is it, or we are using the same variational autoencoder so far? So these things can only be known why. So whenever we see our actual loss function, that loss function contains KL divergence and then MSE. But whether this KL divergence is going to have a appropriate value, that's one big thing. And in the initial investigation of these papers, it was proven like, okay, this variational autoencoder gives very poor performance compared to other state of arts. But this problem was only because of the KL divergence. Whatever the KL divergence we were seeing previously, it was not good. So now, to be intuitive, if each variable in the inferred latent space Z, I mean the bottleneck, is only sensitive to one single generative factor and relatively invariant to other factors, then this kind of problems will happen. So here, the only factor governing is like epsilon. So that should not happen. So we will say this representation is not good. One benefit that often comes with this representation is like a good interpretability, but we are not talking about more interpretability in our machine learning. Rather than it, we are more into more model and more capturing, and then more data, uh, more data output. So for example, a model trained on photos of human faces might capture like a skin, hair, length, emotion kind of things. Whether he is wearing a pair of glass is like relatively independent factor, right? So it is also the same. So we need to have more dependent parameters over here, and then the KL divergence should be like pretty much good enough uh, to settle down. So to this extent, they come up with something called a beta variant, or they call like a beta variational autoencoder. Uh, the thing is like pretty much simple over here. So whatever the KL divergence you are getting, it should be limited. It should be limited. So they come up with the idea called the KL divergence should be limited with should be limited with some parameter of delta, like so that we can call like the KL divergence of the whole value is less than the delta. And then if you see, that's an optimization problem, right? So the KL divergence parameter minus delta is less than 0. So whatever the value we get, we make that one as a optimization problem. So here we have another one more parameter. So the moment the another parameter comes into picture, like the system settles better, and then also we have more control over the divergence things. So that is how the beta variant people were like thought initially, and then they come up with a distangled representation of the things. So we will see how it will go. So the objective, the main objective of beta variant is like, this is our optimization problem. This is what we are seeing, like the KL divergence is like expectation of q, expectation of capital Q over log of p of x, y, and z. So the whole value whatever we are going to see, it should be like less than some delta. So this is the subjected parameter, we subjected optimization problem we have. So they're just constraining the parameter here, and then they're trying to solve the automation problem, so that they end up with a very simplified version. Whatever you are seeing, it's the same. The whole loss looks like the same, but the KL divergence is having a parameter, extra parameter of beta. So this beta is the actual parameter which is going to control the beta variant of a variational autoencoders. So now the loss function is pretty much simple with the parameter of beta, and then this hyperparameter controlling makes the reconstruction quality better. In the initial autoencoders, the reconstruction of the human faces and everything was like pretty good, but the background was like too blurry. If you see any variants of VAE in initial stage, the backgrounds were so bad. But now, like, even we are like in a good shape, like the backgrounds are good. It happened only because of this beta variation, by including an hyperparameter. So now, even now, the beta, whenever it's equal to 1, again it will give to the same standard variant. And whenever it is like higher, then apply stronger constraints on the latent bottleneck. So we are trying to control the actual latent space over there. So it is being controlled with this beta. And sometimes sometimes the reconstruction quality may decrease. I mean, the query quality may decrease, but the overall quality of the image will get enhanced. So there is like if you have higher beta, leads to distanglement, and the cost of reconstruction is only you are going to get, so which is like an autoencoder kind of thing, so which is not good. But there are some benefits. The benefits are like in image generation, it really contributed well, just because of this parameter background blur problem was really gone only because of this beta variant. And uh, after this one, we have another thing called as like a VQ we call like a vector quantized variational autoencoder. Yeah, the VQ, I mean, the VQ variant model learns a discrete latent variable by encoder. Since discrete representation may be a more natural fit for problems like language, speech, or reasoning. So far, in beta variant, it is good for images, but whenever it comes to have a, I mean, the discrete representation, more discrete representation required. It in applications like language, speech, and reasoning kind of thing. That is only possible with VQ variants or like vector quantized variants. And here, uh, the thing is like pretty much simple. We have something called as a code vector. The vector quantization is a method in which we have a k-dimensional vectors will be there in a finite set. We call them as a code vectors. This process is very much simpler to KNN algorithms we see in our traditional ML. So the optimal centroid code, I mean the optimal centroid code vector that a sample should be mapped to is the one with the minimal Euclidean distance. So whatever the code is there, so we have a query, and then query is like very near to the code things, and then we will try to see an optimal centroid code, and then we will try to do the similar kind of thing, like our we call them as like embedding space or code book. Whatever we see in right now, the code books and everything, it's the same kind of analogy being used by vector quantized variational things. But the only thing we see in this one is like another block of code. Okay, I will go through. Like we have a in vector quantization, we have embedding space, and then in embedding space we need to have a lot of code book, and a proper code book needs to be there. And then once you have the proper code book, you can have a proper embeddings, and these embeddings are the real things which is going to help us to search the space and then find the optimal centroid code. And that's how it's going to happen, which is pretty much simple and looks like the nearest neighbor lookup table kind of thing. So the argument is like being expectation minus the centroid one, and then it is going to happen. So if you see here, rather than having a traditional way, here whatever you are having, I mean whatever the image it is there, and then it is going through a encoder model. So you'll be having a space of z. Once you have a space, latent space, you have something called a code book. So there is a code book here, and then your posterior is actually like being optimized over here. Like you have pretty much good query with the code book, and then you are trying to make proper embeddings over here. I mean, this embedding space, you will just go and see the centroid kind of thing, and then get into a better approximation of the latent space. So this is how the variational yeah, was working for us, and the rest of the decoder module is again the same. Okay, yeah, and these are the few preliminary things like how we can have the VQ loss based on the KNNs, and then the actual loss, whatever we are seeing, it remains the same. It won't change much. And then there are some variants also happen in this one, like how you can really go with the embedding vectors and everything by using uh, EMA kind of things. Those things are like pretty similar, but the only contribution here we can see is like having a good code book kind of thing, and then we can have uh, we can have the same loss function computation and everything. And this is another one more variant, like one more variant, but it is also with the same code book kind of things, but with the another conditional things. So this is how the auto encoders was being propagated. I mean, being established in things like a speech and videos. But for images, still have beta version is kind of stable, and variational autoencoders are pretty much good in generative things. So yeah, I think yeah, it's I'm a, yeah, I'm done.
So you're done, sir.
Yeah, it's 4 o'clock. I think it's 1 hour, right?
Okay, fine. Okay, actually, it is for 1.5 hours, but it's okay, fine. We'll take
Oh,
some questions. It should be.
oh, I was so rush.
No, no, ha.
Okay,
Actually, because so much content was there.
okay. I was just looking at my clock every time.
Yeah.
So I
You thought
oh,
it is of 1 hour, actually.
yeah,
Okay, okay. That's why you are in a rush.
yeah, okay, okay.
Fine. Uh, uh,
Shall we go
yeah.
back? Yeah, maybe.
Anybody, please, if you have any questions.
Or we can, yeah, maybe, yeah, if you want we can open my MATLAB, or we can also have some examples, something like that.
You want to show something? Okay,
Yeah,
okay.
that's also kind of okay. For me, like, yeah, and you can, yeah, even we can directly explore to MATLAB examples and everything. That's also pretty much easy.
Yeah.
Yeah. I'm sorry, like
No issues, sir. No issues. Ah,
first we can anyway my system is like starting. We can take some few questions or like few things, and then
ah,
we can go. uh,
if you want to set up something, we will
yes,
take
yes.
some. We'll take some questions. Participants, please. I think in the text box there was some question. How to identify whether the part of an image is a noise?
This yeah, this is a pretty good question, I could say. Yeah, I will tell. Okay. Okay, first thing, if uh, it's like the question is straightforward, like whether the image is like having a noisy image or not. So the standalone question, I mean the standalone thing is like, no machine learning engineer, like they want to train with a good data, and then they want to have a good output kind of thing. But whenever you have some data which is like what I can tell, like a noisy image kind of thing, you can propagate this problem as like anomaly problem. First thing, it's like pretty easy thing. Like I already seen few things, like okay, how I can tell, like if you are having data set of some 100 images, like good images, and then few of them are like not good, first try to tag them as an anomaly, and then try to solve the problem. That's a easiest solution, because whatever the gen as you are seeing, gen as are like very much tuned to it, I mean tuned, so that even if you are giving some corrupted image, it will try to enhance the image. So that kind of problem is happening. So don't try to solve that kind of questions with gen AI, any pre-trained things. So that's my first intuition I want to tell. portray this one as an anomaly problem, and I will show one good example. Yeah, even I have gone through this kind of thing. Uh, I will share. Yes, anomaly detection. Open in MATLAB online. Okay. Can I post here? Uh, where I need to give some solution like in text. Is there any some text box or something here? Yes. Just now I pasted one GitHub repo. Just now I pasted one GitHub repo. If you can see, uh, even variational autoencoders they were trying to use for anomaly detections. So it's but the outputs were like not that good. I verified long back to this GitHub repo. You please try to have a look. This is one thing, and then the part of the image. Yeah. Any other query? I was feeling hard to set up my system. Okay.
Sir, are you
Yeah,
showing
please.
something?
I'm just trying to set up still.
Okay, 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 fine, fine. I thought.
But this kind of problems, I would suggest to have proper label, like then system can learn. That's the only thing. But don't try to directly give anomalies as an image and then try to expect some output. It won't happen. It will only try to recorrect it. Yeah, if the parameters are like highly tuned. I'm sorry, like my MATLAB was like not supporting exactly. It's telling like adding path to installer, GStreamer, or like some library issue. Yeah, I'm sorry. Yeah,
No,
I,
it's okay.
I was also excited to show some of our previous works.
Yeah, yeah. You can some documents later as well if you want to share something.
No, it's okay. It's progress work. I'm sorry for that.
Okay, no issue. Actually, I told you actually only autoencoders and variational autoencoders, but beyond that, you have taken many much more.
And actually, it's my mistake. I have seen, but
No, no, it's okay. So you can focus. You can slide. You
yeah,
can.
I can. What is the role of VAE in deep fake?
Yeah, what something like that, or
Is okay. Then just hello, hello.
Yes, sir.
Hello. Yeah. Yeah. Okay. I will take this problem in a different way. Like a deep fake, if you are trying to see like deep fake as a whole scene for only faces, it's like pretty much easy problem to the system. Why? Because whatever the VAP, I mean VAE, so far we have seen, it is like very much highly trained to facial images, and then it can able to create good lower dimensional latent spaces, and easily it can create a from the lower dimensional space even with a slight variation in our latent space with the smaller values, we can get different things, like even the expression pose kind of things are like pretty much easy. So deep fake for a face is a straight away solution with the current era. I mean, with the current era of encoders, it is like totally possible. But there is another different whole research area here. If you see, if I'm correct, maybe few of the content, I mean, online content, everything, people used to show like instead of 5 fingers, when they are reporting continuously, they are reporting like Gen AI was not working. Instead of 5 fingers, it was telling like a sixth finger to the person and everything. It is failing there. Why? Why exactly is like our database, like the kind of database we have seen so far is with the mostly with the human faces and everything. So our systems were like totally trained for the faces and everything, and it can able to create very much lower dimensional latent space, and then it can create a good key features for the faces. It is possible, but we won't see any uh, I mean, dedicated data sets and everything for the human hands and everything, right? So that is where it is like failing. So if you see deep fake as a whole system, or like a uh, whole video, or like a whole system, like if you want to analyze it for the whole person, yeah, it will fail. It will obviously fail, just because our databases are totally enriched for the faces, dresses kind of thing, but not with the very simplified things like hands, hand poses, or like even nails, or some nudity kind of things. So this is where it fails. And yeah, if someone is interested, this deepfake problem can be created, can be taken to one level by making one proper data set with the different hand expressions kind of thing, and then try to embed the whole information again in our data set, and then try to make a queries. So that's one way you can address the problem. It's an open problem as well. It's an open problem as well, and even you won't see any data set pertaining to only hands, or like wrinkles, such kind of things. Yeah, someone who posted it, it is good to take some that kind of research topic. It will solve some sort of problems which are we are seeing with the Sora right now. Yes. And another question: can you suggest a book for variational order? Yeah, yeah. I will give you a very good material. Exactly. I was thinking of it. Wherever we prepare, you should go. This thing you can have it, and then I think everyone is aware about RBC Boreals. That RBC Boreals dedicated one chapter, especially for a variational autoencoders. The second link, whatever I'm providing, this is one of the best thing I have gone through in recent times. For variational autoencoders, you can see whole lot of things, like they started with spaces, mixtures, and then they will try to go go in other things like post they will tell posteriors expression maximization, and then they will try to tell you like how this loss came into picture, and ELBO derivation, Jensen's inequality, everything, but in a very simplified way. It's only in 2-3 paragraphs of things, so with a good figures. I would suggest to go for this tutorial rather than having book. And it is also pretty much standard thing, and they use the same nomenclature as the textbooks, like image with X, space with Z, and kind of thing. So it is good. Yeah, yeah, the second one is good in my opinion. And uh, also for I mean, machine learning enthusiasts, I would suggest to have one bookmark in your things, which is called as a understanding deep learning. There is something called UDL book. Okay, yeah. My screen is still in sharing mode, right? Okay, then I will show this thing. Yeah, yeah, you are seeing like a UDL book, right? So this is one of the best things you can have. You will learn whole lot of concepts directly in a collabs. So this is how even we used to do, and we get our students, like if you are looking for encoder, my screen is visible, right? Or am I just
Yes, yes,
doing?
yes.
Yes, yes, visible.
Yeah, if you are like interested, just go for efficient encoders, just go to collabs, and then you can do these concepts are like pretty much straightforward, and then you can see the implementation. And once you are done, if you are interested to prepare some presentations or anything, I would say go here. And then, for example, for variation autoencoders, I didn't create any of the pictures. There is something called a PDF over here. If you click on PDF, you will get the only images, like whatever we images we use, and svgs we can manipulate for your research work. If you have svg, you can directly open in a draw.io or like inkscape, and then you can make smaller modifications for your diagrams, and then you can make a new one. So it is good. uh, and then you can scroll down, and once you scroll down, here you have a theoretical kind of things. For example, this is a encoder decoder. I will show, yeah, variational encoder. Just by giving a click, yeah, you will end up with autoencoders. They will start, they don't make you more complicated most of the thing. This is like pretty much easy, and then you will just scroll down. They will show what essentially is happening. And then, yeah, if someone is like teaching, I would suggest to go through this kind of material. So you can cover the whole lot of things in 2 hours or 3 hours of lecture. And the kind of writing is like straightforward. They don't make any too much ambiguity in explaining the things. You can see it's pretty much easy. I would suggest everyone to follow understanding deep learning. This is pretty much awesome. You will get code, you will get the presentations, you will get the tutorial, everything here. Yeah. Please share that link. Yeah, I did it. I think, yeah, this one I need to share. Yeah, this one, yeah, it will work. UDL book. That's it. And if someone is pursuing research topics, yeah, feel free to ask. Basically, I'm from sensing background. I usually work with uh, camera data. Like usually, I work with the camera data, thermal data, and then leader point clouds. And most of the time, I work on uh, as simple CNNs, lightweight CNNs. And coming to advanced topics, we usually work in a transformers kind of thing. But in research topics, don't go too much into encoders kind of thing. The area was totally saturated, and yeah, we can't do. But application wise, it is there. Still, lot of opening is there in research applications. And even lot of gap is there in a ML, especially for a data creation and then application. So always try. I always suggest people to look for the data gap rather than the research gap. Please try to see which kind of data is not available, and then try to make preliminary things like how to get into the proper data. So get the data and then do on the data, and then you can straight away prove, like, okay, this is the exact gap, and this is what it needs to be done. Proper analyzing the data, statistically, is kind of good topic nowadays, rather than a whole lot mathematics and other things. Yeah, this is the only thing I want to tell. Yeah.
Yeah, any more? One question from my side, sir.
Yes, please.
How can these VAEs, variational autoencoders, or their improvements can be combined? Are we combine, or can we combine these with another generative models like GAN?
Yeah. It's pretty much easy. Okay, I will tell one beautiful thing. For example, whatever model you are trying to do, it's like it's basically encode decode model, right? So in this one, if you are trying to do something like a multi-sensor setup or multi-data setup, then you can combine them very easily. If you are having a model and if your model is being trained with one set of data, let us assume I am having three different models, three independent models. Let us assume three independent models. One independent model is only responsible and which is being trained with a human behavior or human emotions or human faces kind of thing. Okay, and I am having another one more model which is being totally trained with the scenario, I mean scenes, the whole background scenes and everything. So if you are having two different things, but we need to combine them, right? So whenever you are capturing a human face and everything, which you need to be done in a very zoomed fashion, but whenever you have to take a scenario or scene, natural images, you have to take in a very zoom out fashion. But how these two can be done at the same time? Yeah, these two can be done in the same time just by combining our networks. So we can make a uh, en- encode decode model, another encode decode parallel model, and then concatenation of information. So whatever the features we are seeing, we have to make another one more block where the G spaces will be like again feature engineering. It is similar to a feature engineering we do in CNNs. Once we got into some features, these features can be concatenated with another feature vector, right? So two feature vectors, if we concatenate in a machine learning, we call them, we sometimes we call them as a fusion as well. So this is also some sort of fusion. So once you have Z from another model and another Z from another model, then just try to concatenate them in a proper way and then give some other small model there. So retrain, it's a retrain kind of thing, and then apply a decode model, then you will get a very beautiful results. Yeah, we worked on this kind of models. We call them as a fusion models. In fusion models, uh, pretty much the very much simpler thing is like take two models, train them, get the feature vectors, concatenate the feature vectors, and again train them with a smaller layers, and then go for a decode model. It will work.
Thank you.
Yeah, and more precise, can transformers be used in finding anomalies in images and or videos? Yeah, exactly. Yeah, a transformer can able to do it. But we are seeing in this era, we are seeing transformers are making more mistakes. ChatGPT, initial versions of ChatGPT and everything, we were like, yeah, anomalies we can. Yeah, this is also possible. And I'm wondering if someone is working on a anything like retraining the things, or I mean, retrain. This trend is there, right? So rather than that, there is some other trend right now started, which is called as a detraining. So whatever the model, like the transformers or like gen, whatever we are seeing now, they want to start something called a detraining model. So our model is trained for some time or like for some months, and now we want to detrain it. We don't want it to learn all the recent informations. Just de-learn the things and then again learn the things. This is one kind of pattern we are going to see in the next 5 years or 6 years. It's also one good topic, detraining. Yeah, so yeah, if someone's looking for some research topics, please try to look into those aspects as well. And anything, this time you are telling about image or what space exactly? Can transformers be useful in finding anomalies in images or videos? Okay, this is kind of okay. Anomalies. One thing is like you can directly download the pre-trained version and then first see whether your anomaly is like uh, really not working or not. That is the one good thing we have to do in this kind of case, first thing. So it is something like, what are the pre-trained models we are seeing? They did with a good set of data. So all of a sudden we have some anomaly data. So rather than trying to build something new, first test your data, just test your anomaly data on your pre-trained models. Whenever the pre-trained model is giving very bad result, if it is giving very bad result, it means yes, it is only telling it is an anomaly. So directly you are getting an information. You can observe that one by reconstruction errors and other methods as well. So that's the first thing you have to do. In case if it is not doing well, and if it is only manipulating the image and trying to give some good sort of image, then we have to think of a formulating the problem. Formulating the problem in a data way, like more anomalies we have to create, and then we have to tell like this is a anomaly one in a encode decode way, so that the embeddings will be uploaded there, and then it will only learn like, okay, enough a number of anomaly embeddings are there, so it will try to learn. I will tell one small example. For example, the whole network is with human faces, and all of a sudden you are trying to give some dog or something. It will throw an error, right? It will tell like, oh, no, no, this is not the good thing. So in that way, we can learn it. You can make some justification like, okay, it is only telling as an anomaly. But even in case in the human faces and everything, if they are taking some pictures with along with some scenes, dogs and everything, it it may or may not tell the exactness of your problem. Then in that case, what you have to do, we have to label them, and we have to create more data set of the dogs, so that it will learn in a proper way and it will tell as an anomaly. So in that case, we have to tag all the dogs as an anomalies, so that it will flag it. So these two are the straightforward ways to solve it. And you have to use a reconstruction error. It will that score will tell you how much is there. And then anomalies, I mean the manipulated images by Reddit tools. Okay, yeah, this one is also good. Okay, you are talking about the reconstructed image itself. Okay, so you have some reconstructed image, some manipulated image you have, and then you want to see whether that reconstructed image is actual reconstructed image, or it is something like taking the content from ChatGPT and seeing whether it is like ChatGPT generated one or not. Yes, okay. I'm not exactly sure how exactly look into this problem. Yeah, but yeah, usually we quantify the manipulated image with the scores, and we will see whether the manipulated image is very near to our actual image or not. But you are telling like manipulated image should be quantified. Okay. Yeah, maybe with the metrics it is not possible. With metrics, maybe because all the metrics whatever we are seeing, it is working the same way. Always we'll try to minimize the matrices and then try to get the manipulated image as good as possible. But yeah, I'm not exactly sure how to get into this problem. Yeah, sorry. I will just I will also see to Mahendra Kambalia. Sorry.
Fine. Any more? Okay, then we'll conclude. Thank you very much, sir.
Yes,
Thank you
thanks.
for your explanation of the very important concept from their mathematical foundations again to the practical applications in generative AI. You have truly highlighted a very important concept, and the clarity with which you have explained all these topics with the mathematical foundations was very good. And again, you have given some guidelines for the research as well. So thank you very much, sir. On the behalf of all the participants, I thank you. Thank you very much.
Yeah, thank you.
Sir, please kindly share your PPT, sir.
Yeah, I will. Yeah, where can I drop it? How?
Okay. My
Mail,
mail.
mail. Is it
Uh,
okay to mail it? Okay.
yeah.
Could you please spell out your mail, or like you can provide in a chat box?
Yeah.
Control C. PPT. I gave a meta information of PPT VAN, variation autoencoder. Yeah. Yeah, I can check it, sir. It's done. Yeah, thank you.
Thank you very much.
Thank you, sir.
Okay.
Yeah, thanks for invitation. See you.
See you.